Good day, class. In this video, I will going to discuss partial fraction expansion, or it is also known as partial fraction decomposition. So this concept is used to represent a certain complex fraction as a sum of simpler or partial fractions. Now, from the previous lesson, we discussed on how to combine two fractions in order to create a complex fraction. So this time we do the reverse, in which on the left side right here we are given a complex fraction x plus 2 over x squared minus 7x plus 12, and then we're going to split this one into simpler or partial fractions as shown on the right. Now I will going to introduce you two methods in performing partial fraction expansion. The first one is the cover-up method, and the second one is the cross multiplication method. For the cover-up method, it is easy to manipulate, and it is faster compared to the cross multiplication method. But for the cover-up method, it is only limited to distinct um, factors, whereas for cross multiplication method, it can be applied to all complex fractions with repeating factors of its denominator. Okay, so the first step in performing partial fraction is to determine whether the given complex fraction contains an expression in the numerator that has a lesser degree compared to the expression in the denominator. So in our first example, it is obvious that the degree of the expression in the numerator is equal to the degree of the expression in the denominator. So we're going to modify this one so that the degree of the numerator would be lesser than the degree of the denominator. So the first step is to perform long division. We're in performing long division, we're going to divide the numerator 4x squared plus 21x plus 21 divided by the denominator x squared plus 4x plus 3. So for long division, your goal is to multiply a certain number or expression so that the first term of our dividend will be cancelled out. So the first term of our divisor is x squared, so therefore we're going to multiply by a number 4, and then you need to distribute this to the expression in our divisor, and then write your answer below our dividend. So we have 4 times 3, that's 12. 4 times 4x is 16x, and we have 4 times x squared is 4x squared. Now the operation here is subtraction, so the first term will be 0, and then for the second term we have 5x, and then the last term is plus 9. So for our long division, 4 is our answer, and then 5x plus 9 is our remainder. Notice that the expression of our remainder has a degree that is lesser than our divisor. So therefore, we can write the answer from our long division into this form. We have 4 plus the remainder all over the divisor, that is x squared plus 3. Now, for our partial fraction expansion, we are concerned on this term. Now, luckily, after performing long division, we have just transformed our given complex fraction into a fraction in which the numerator has already a lesser degree compared to the denominator. So the next step is to factor out completely the denominator and get the partial fractions. So we have here 4 plus 5x plus 9 all over this expression. So we're going to factor out x squared plus 4x plus 3. So this is a trinomial. Now, I already discussed to you some steps in factoring, but I think you cannot apply special polynomials here. The most um, the most easiest method to be used here is factoring by trial and error. So the factor for x squared plus 4x, the factors are x plus 1 and x plus 3. Now in generating functions, um, it is based on the number of factors. So if we have factors, then we also have two simpler fractions or partial fractions. And then there is a pattern here. So if the degree of the denominator is 1, so take a look at the first partial fraction. We have a over x plus 1. So x plus 1 has a degree of 1. So the numerator takes the constant value, and let's say a. Okay, a here is constant. Then our second partial fraction is for the factor x plus 3. And since the degree is still 1, so we use a constant value for our numerator, and then we assign another constant, that is b. Now if the degree of the denominator is 2, that is x squared, for example x squared plus 2, so therefore your form ax plus b. Now if the degree is 3, then the numerator takes the form ax squared plus bx plus c. So the pattern here is that as the degree of the denominator increases by uh, n, so the degree of your numerator should be um, increased by n minus 1. Okay. So next is we're going to use the cover up method to solve for the unknowns a and b. So we have here the partial fractions, and then let's start by solving the value of a. So to solve for a, you're going to write the expression, the given complex fraction, but make sure that the denominator should be in a factored form. So you have x plus 1 and x plus 3. Now, uh, here is the exciting part. So it is the reason why it is called cover up method, because we're going to cover the factor that is used for our first partial fraction. So for a, the factor is x plus 1. So we're going to cover that factor. And then, of course, since we want to know the value of a, then we're going to assign a value of our x here. So where can we find the value of x? So we're going to find it by equating the factor that we have just covered, that is x plus 1, to 0. So solving for x, that is negative 1. So we're going to substitute this value in our expression here. So we have a equals 5 times negative 1 plus 9 all over negative 1 plus 3. So the answer is 2. So our a is equals to 2. So this is how you're going to perform the cover up method. Now let's try for variable b. So the same as a, write the expression, then cover the factor that is used for our second partial fraction or simple fraction, that is for b, and then equate the factor for b, that is x plus 3, to 0, and then solve for x. Our x here is equals to negative 3, and then substitute this value to our expression. So our b is equals to 3. Therefore, the partial fractions for our given complex fraction is equal to 4 plus 2 over x plus 1 plus 3 over x plus 3. Now let's try another example. So we have here 5x cubed plus 15x squared plus 9x minus 3 all over x squared plus 3x plus 2. Again, the first step in performing partial fraction decomposition is to determine whether the degree of the expression in the numerator is already lesser than the degree of the expression in the denominator. Now, in this example, the degree of the expression in the numerator is still greater than the degree of the expression in the denominator, because in the numerator the degree is 3, and then in the denominator the highest degree is 2. So 3 is greater than 2. Now if that is the case, then we need to perform first long division. So we're going to divide the numerator, which is this expression, by the denominator, which is this expression. Since since the first term of our dividend is 5x cubed, then the first term of our divisor is x squared. So to eliminate 5x cubed, we're going to multiply 5x to our divisor. Now, the next step is to distribute 5x to each of the terms in our divisor, and then you're going to write your answer below the dividend. So the operation here is subtraction. So 5x cubed minus 5x cubed is 0, 15x squared minus 15x squared, 0. So therefore, we have 9x minus 10x, that's negative x, and then bring down the negative 3 here, bring down the constant. Now, as you can see, the remainder has a degree that is lesser than the degree of the divisor. So you can now terminate the long division. But if you perform long division and then if you found out that your remainder or the degree of your remainder is still greater than the divisor, then um, you're going to continue the long division. But if the degree of your remainder is already lesser than, again, equal is still not okay. So if the degree of the remainder is lesser than the degree of the divisor, then that is the time that you should terminate the long division. So therefore, the uh, the answer for long division is equal to 5x plus the remainder divided by the given divisor. So the fraction decomposition is focused on the second term for this expression. So next, we're going to factor out completely the denominator. So our denominator here is x squared plus 3x plus 2. By trial and error method, the factors are x plus 2 and x plus 1. You can also check these factors if they are correct by performing FOIL method. Okay, that is square the first term of the binomial, that is x times x is x squared, and then multiply the last terms of the binomial, that's 2 times 1, that's equal to the last term of the trinomial. And then to get the middle term, you're going to get the product of the inner and the outer terms of the binomial, and then add the two products, and that will result to 3x. Okay, so once we have already factored out the denominator completely, the next step is to generate the partial fractions in terms of the constant. So we have a over x plus 2 plus b over x plus 1. So the reason why we still use the constant, because again, by following our rule that I have just shown you from the previous example, since the degree of the denominator is 1, so the numerator takes the constant value, okay, from the first rule. Next is to solve for the unknowns a and b. Again, still use the cover up method. So for a, we're going to write the expression in factored form, and then need to cover up the factor of a to 0. Then solve for x, that is negative 2. And then substitute this value to our expression right here. So you will arrive an answer for a that is equal to 1. Then for variable b, again, write the given complex fraction in factored form for the denominator, and then cover the factor for b, and then equate the denominator of b to 0, and then solve for x. Then substitute this value to our given expression. You will come up a value of b that is equal to negative 2. Therefore, our partial fractions are 1 over x plus 2 minus 2 over x plus 1. Now, let's try the third example, but take note, for rational expression whose denominator contains repeated factors, we're going to use the cross multiplication method instead of the cover up method. So that is for the second step of our partial fraction expansion or decomposition. If you found out that we you have a repeated factors, then do not use the cover up method. Use cross multiplication method instead. Okay, so for our third example, by inspection, the degree of the numerator is already lesser than the degree of the expression in the denominator. So therefore, we're going to skip the first method, that is performing long division. So we will proceed directly to the second method, that is we're going to factor out completely the denominator. So the factors for x cubed plus 4x squared plus 4x, we know that we have a common factor for each term, that is x. So extract the x variable, and then what's left is x squared plus 4x plus 4, and that is a perfect square trinomial. That is why we have a repeated factor of x plus 2. Now, by following the rule in generating the partial fraction, we're going to base the number of fractions by the number of factors that is being generated in the denominator. So in our denominator we have three factors, so therefore we must have three partial fractions or simple fractions. So we have for the first factor, that is x, so the degree is 1, therefore we take the constant value a. Then for the second factor, that's x plus 2, so we have b. Then we have for the third partial fraction, that is x plus 2 squared, and still the degree is 1, so we use c. Now for um, repeated factors, please do not forget these two rules. So if the factor is repeated n times, now in our example, we have a repeated factor x plus 2. So it is repeated twice, as you can see by its exponent 2. So there will be n number of fractions being produced. So for x plus 2 factor, we have two partial fractions. We have the b over x plus 2 and then c over x plus 2 squared. So if we have a repeated factor that is repeated thrice, that is 3 times, so for x plus 2, so we need to add plus d over x plus 2 cubed. Okay, that's the rule. So next is the exponents of this n number of fractions increase from 1 to n. As you can see, for x plus 2, we start for b, so that's x plus 2 raised to 1. We have an invisible exponent here, 1. And then followed by c over x plus 2, but this time, again, the exponents of this n number of fractions increase from 1 to n. So we start at 1, then the next is 2. And we terminate in this, or we terminate at this point because we already reached the maximum exponent that is equal to 2. So the, in other cases, say for example, if x plus 2 is repeated thrice, so therefore we're going to terminate our partial fraction up to uh, let's say d over x plus 2 raised to the power of 3. Okay, next is for cross multiplication method. It's a different thing, so it is different from the cover up method, because for the cover up method, we base the calculation for the unknown variable to the original expression, and then we just simply cover up the factors. But for cross multiplication method, the technique here is by using algebraic manipulations. So for this method, we're going to multiply both sides of the equation by the denominator of the given complex fraction, and that is x times x plus 2 squared. Okay, so this is our expression or our equation. So this complex fraction is equal to its corresponding partial fractions. Now, for cross multiplication method, our goal is to eliminate the fractions. So therefore, we're going to multiply both sides by this expression. Okay, so we're going to distribute this to each of the terms of this equation. So for the left side of the equation, what's left is only the numerator, that is 7x squared plus 22x plus 8. And then for the first term of our partial fraction, so we have a over x multiplied by this one. So what's left is the second factor, that is x plus 2 squared. Then for the second partial fraction, we have bx times x plus 2. And then for the third, the x plus 2 raised to the power of 2 will be cancelled out. So what's left is only c multiplied by x. The next step is to simplify the right side of the equation. We're going to focus our simplification on the right side, right here, and then combine like terms. So for a times x squared plus, I mean, a times x plus 2 squared, so we're going to expand this binomial. So we have a times x squared plus 4x plus 4. And then for bx times, sorry, x plus 2, simply distribute bx to each of the term inside the parentheses. So you have bx squared plus 2bx and then plus cx. Next is distribute the a inside this trinomial. So we have ax squared plus 4ax plus 4a and then plus bx squared until cx. Next is, okay, this is a continuation. So we're going to combine like terms. That is, combine the term that contains x squared. So you have a plus b x squared, and then for x we have the terms for ax and 2bx, so we and also cx, so you have 4a plus 2b plus c multiplied by x, and we only have one term for the constant, that is 4a. Next is, we're going to solve for um, the unknown variables. So to do that, we're going to compare the two sides of the equation. So on the left side, we have 7x squared plus 22x plus 8. And on the right side, we have just combined uh, all the terms that are alike. So therefore, by inspection, for the coefficient of x squared, the left side and the right side should be equal. So a plus b should be equal to 7. And then for the coefficient of x, that is 4a plus 2b plus c, it should be equal to the coefficient of x on the left side, that is 22. And also, the constant of the left side, I mean on the right side of the equation, that is 4a, should be equal to the constant of the left side of the equation, and that is 8. So we're going to equate um, these coefficients. So let's start with the constant. Now the reason why I start with the constant, because we can directly solve for a. So we have 4a equals 8, therefore a is equals to 2. Next, I'm gonna choose the coefficient of the x squared, because we already have a value for a, then we can solve directly for b. We have a plus b is equal to 7. So b is equal to 7 minus a, and we all know that a is 2, therefore b is equals to 5. Next is for the coefficient of x. So we have 4a plus 2b plus c is equals to 22. Since we already have values for a and b, we can solve directly for c. So transpose these two terms, then um, substitute the values of a and b. So we have c is equals to 4. Next is generating the final partial fractions. So therefore, this given complex fraction has a partial fractions of 2 over x, so that is the value of our a, that is 2, plus 5 over x plus 2, plus 4 over x plus 2 squared. Okay, so let's have another example. So this one is um, we're going to apply the cross multiplication method. So by inspection, the degree of the expression in the numerator is already lesser than the degree of the expression in the denominator. So therefore, we're going to skip the first step, that is performing long division. So we'll go directly to the factoring of the expression in the denominator. So the factors of x cubed plus 9x squared plus 24x plus 16. So you can do factoring by grouping or by trial and error. So we have x plus 1 times x plus 4 raised to the power of 2. As you notice, we have a repeated factor, that is x plus 4. And then in generating the partial fractions, for partial fractions to the number of factors that is being produced in the denominator. So we have 3 factors here. So expect 3 partial fractions. Okay. So since the factor is sorry, repeated twice, so our n is equals to 2. So therefore, we will start the exponent of our denominator for x plus 4 by 1, and then we're going to terminate that one by x plus 4 raised to the power of 2. So these are our partial fractions. A over the first factor, and then b over the repeated factor x plus 4, then plus c over the repeated factor x plus 4, but we're going to increase the exponent by 1. Okay, so next is to perform the cross multiplication method. So to eliminate the fraction, we're going to multiply both sides of this equation by the denominator of the given complex fraction in factored form, that is x plus 1 times x plus 4 squared. So we're going to multiply this to the left side of the equation. What's left is the expression in the numerator. And then for the first term of our partial fraction, what's left is only the factor x plus 4 squared. And then for b, we have x plus 1 and x plus 4. And then for the last partial fraction, for c, x plus 4 raised to the power of 2 will be cancelled out. So what's left is x plus 1. The next step is to simplify the right side of the equation, which is this one. So we're going to expand the x plus 4 squared into x squared plus 8x plus 16. And then for b, we're going to multiply these two binomial. You can use FOIL method in order to generate x squared plus 5x plus 4. And then for the last term, simply distribute c to each of the terms in this binomial. So we have cx plus c. Next, distribute a to each of the terms in our trinomial as well as for b. So you have this expression. Next is to combine like terms. So for x squared, we only have two terms, that is a plus b. And then for the term that contains x, we have 8a, we have 5b, and then we have c. And then for the constant, we have three terms, 16a, 4b, and c. Next is to compare the um, two expressions on the left side of the equation and on the right side of the equation. Now let's start with x squared. So a plus b, so the coefficients for x squared on the right side should be equal to the coefficient of the x squared on the left side, that is equal to 5. So we can have b is equal to 5 minus a. So we cannot solve directly for the values of a and b. So let's stay this equation as is. Then proceed to the coefficient of x squared. So we have 8a plus 5b plus c equals 38. Since we have a value for b that is in terms of a, so we can substitute this one to our variable b on the x. So you have 5 times 5 minus a. Then combine the terms that contains a. So we have 8a minus 5a, that is 3a. Then transpose 25 on the right side. So we have 3a plus c equals 38 minus 25. So we have 3a plus c equals 13. Next, let's proceed to the constant. So we have 16a plus 4b plus c equals 60. Since we already have an expression for b in terms of a, so we can substitute this one to our equation for the constant. So we have 16a plus 4 times 5a minus a, 5 minus a. Then combine like terms. So we have 12a plus c equals 40. So we have 3a plus c equals 13. We have 12a plus c equals 40. So in this equation, we can solve for a in terms of c, and then use that one or substitute that expression for a to this equation and then solve for c. Okay, so again, I have a list of the equations that we have just derived from the previous slide. So we have b equals 5 minus a, we have 3a plus c equals 13, we have 12a plus c equals 40. So let's start with 3a plus c equals 13. So c equals to this expression. Then let's proceed to 12a plus c equals 40. So 12a plus our c is 13 minus 3a. So substitute that one right here. So we have 9a equals to this expression. So we have a is equals to 3. So we already have a value for a. Then we can substitute this one to this equation to solve for c. So we have c is equals to 4. Next, we can also solve for b because we already have a value of a that is 3. So we have 5 minus 3, that is 2. Therefore, our b is equals to 2. Next is generating the final partial fractions. So by using the values of a, b, and c, so we have these partial fractions 3 over x plus 1 plus 2 over x plus 4 plus 4 over x plus 4 raised to the power of 2. Now let's have another example. We have here 5x squared plus 3x plus 7 all over x cubed plus x squared plus 2x plus 2. So since the degree of the numerator is already lesser than the denominator, so we'll proceed to the next step, that is factor out completely the denominator. So the factors of our denominator are x plus 1 and x squared plus 2. Notice that one of the factors of our denominator contains an expression of the second degree. So we have x squared plus 2. So therefore, we're going to use the second rule, which is shown right here, which is shown below. So if the degree of the denominator is 2, the numerator takes the form ax plus b. So in generating the partial fraction for x squared plus 2, the numerator should be of the form ax plus b. So we're going to apply this one. So for x plus 1, since the degree is 1, so simply going to take the constant value a. Then for x squared plus 2, since the degree is 2, therefore the format should be bx plus c. That is, we have, or that is the numerator is of the first degree. Okay, next is to solve for the unknowns a, b, and c. Now we're going to use the cross multiplication method here because it is more convenient compared to the cover up method. So we're going to eliminate the fraction. So to eliminate the fraction, we're going to multiply both sides of the equation by the factors of the denominator of the given complex fraction. That is x plus 1 times x squared plus 2x, plus 2. Okay? So we're going to distribute this expression to each of the terms in the given equation. So for the left side of the equation, what's left is only the numerator, that is 5x squared plus 3x plus 7. And then for the first partial fraction, what's left is only a multiplied by x squared plus 2 because x plus 1 will be cancelled out. Then for the second term, or for our second partial fraction, the x squared plus 2 will be cancelled out. So what's left is only the numerator multiplied by x plus 1. Next is to simplify the right side of the equation. So we can distribute a to each of the terms in this binomial. So we have ax squared plus 2a. Then for bx plus c, we're going to multiply this one to x plus 1. You can use the FOIL method. So we have bx squared plus bx plus cx plus c. Simplifying further, so we can combine the terms that contains x squared. So we have a plus b. And then for the x terms, we have b plus cx. And then we have two constants. That is, or these are 2a and c. Next is we're going to compare the two sides of the equation. So a plus b, the coefficient of x squared should be equal to 5. And then the coefficient of x, that is b plus c, should be equal to 3. And the same with the constant, that is c plus 2a on the right side should be equal to the constant on the left side, that is 7. So let's start by equating the coefficients for x squared. So we have a plus b is equal to 5. So a is equal to 5 minus b. For x, we have b plus c equals 3. And then we have c is equals to 3 minus b. Then for the constant, we have c plus 2 equals 7. Now, for the constant, since we already have an expression for a in terms of b, so you can, um, I mean, um, yes, since we already have an expression for a in terms of b, so we can substitute this one to our equation for the constant as well as c, because we already have an expression for c in terms of b. So therefore, we now have an equation that contains a single unknown, and that is b. So we can solve directly for b. Now, simplifying this one, we have 3 minus b plus 10 minus 2b. So we just distribute the 2 to each of the terms inside this parenthesis. So we have negative 3b equals to 7 minus 3 minus 10. So we have negative 3b equals negative 6. Therefore, b is equals to 2. Since we already have a value for b, now we can substitute this one to this equation and also to this equation to solve for a and c simultaneously. So for a, we have 5 minus 2, that is 3. Then for c, we have 3 minus 2, that is 1. Therefore, our final partial fractions are 3 over x plus 1 and then 2x plus 1 all over x squared plus 2. Okay, so that's it for this topic. Thank you and God bless.